Log rules. So I'm going to show you the product rule and the quotient rule today. And I'm going to illustrate this with an example. Suppose you want to do 70 divided by 17, and you want this accurate to 4 decimal places. Now, you know how to do that. You take 70, divide it by 17, and then you look at this and say, well, I can't divide 17 into 7, so I've got to divide it into 70, and 20 goes into 63 times, so that's probably a 3, and then multiply that out, so you've got 21, and 3 times 1 is 3, and 2 more is 5, and then subtract them, and that's giving me 19, so I could have fit one more, so we'll put a 4 in there, and so on. And long division is just very annoying and takes a long time. There's got to be a better way. Well, obviously the better way is to use your calculator or a computer. However, back in the day, before such things existed, your grandparents, or maybe your great-grandparents now, would have used log tables. And a log table is a book that contains pages, and within those pages are, well, that's sort of a newer one. Here, this is a photograph of an old one. And this gives you the log of various numbers. So here, for example, the log of 13 is 1.1137. The log of 13.2 is 1.1206, and so on. So you can just look all those values up within the table. That's nice, but how is that helpful in terms of doing long division? How would that allow your grandparents to avoid doing long division and yet get the right answer? There's a log rule, and the log rule is, well, there are a few of them, but we're going to look at the quotient rule. And that is the log of a quotient. So the log of, let's say, A divided by B is equal to the log of A minus the log of B. This is the quotient rule for logs. Similarly, there's the product rule for logs. The log of A times B is equal to the log of A plus the log of B. You see, using logs allows you to turn division into subtraction and allows you to turn multiplication into addition. The reason why is, remember, the log gives you the exponent, and these are analogous. Well, they're really just sort of other versions, or the log version of these rules here. If you have, say, 10 to the A, and you divide that by 10 to the B, that's equal to 10 to the A minus B. So dividing powers can be done by subtracting exponents, but the log gives you the exponent. So when you're dividing numbers and you take the log of them, that is the same number as subtracting the logs. Okay, so how is this useful? We're going to use these log tables and this log rule here to figure out what 70 divided by 17 is, quickly and accurately to within 4 decimal places. So I start out with my question. I've got 70 divided by 17, and I'm going to take the log of it. The log of A divided by B is equal to the log of A, so this is the log of 70, minus the log of 17. So I use this rule here. The log of A divided by B is equal to the log of A minus the log of B. So I just need the log of 70 and the log of 17. So I'll go over to my table. And sorry, I'm old, taking time to use this whiteboard, learn how to use this whiteboard. Okay, here we go. So the log of 70 is 1.8451. I know it says 0.8451. I'm assuming if you're using this, you know it's got to be at least a 1. 10 to the exponent 1 is 10. 10 to the exponent 2 is 100. So if you're looking for a number between 10 and 100's log, it's got to be 1 point something. The log of 70 is 1.8451. The log of 17 is 1.2304. Okay, so I've taken the computationally costly problem of 70 divided by 17. Remember, we'd have to go through long division to do it. I don't know, I kind of scratched out the start of it, and then I guess I erased that. I was looking for it. Okay, so you've got the log of 70 divided by 17 is the log of 70 minus the log of 17, which is 1.8451 minus 1.2304. So we could just do this by hand real easy. So it's 0.6147. Okay, so does that tell me 70 divided by 17? No, it tells me that the log of 70 divided by 17 is equal to 0.6147. And I'm just going to grab my charger before my computer dies on me here. So now I have the log of 70 over 17 is 0.6147. So 70 divided by 17, I'm just going to have to figure out what has a log of 0.6147. So I've got this table here. I'm going to look for the number closest to 0.6147. .6149 is 4.12, and 0.6138 is 4.11. So I'm going to say this is 4.12. So my answer is that this is equal to 4.12. Now, we can check that with a calculator. 70 divided by 17 is 4.117. It would round to 4.12. So we've accurately got that answer. Notice, we did not have to actually do any division to accomplish this division. We simply looked up the log of the divisor and the dividend, and then we subtracted them and then converted it back. So that would have been back in the day how your grandparents or great-grandparents would have calculated as a shortcut long division questions. So in your book, you've learned in this chapter, as you read through it, you're going to see these two. This is the product rule. The log of A times B is equal to the log of A plus the log of B. And the log of A divided by B is the log of A minus the log of B. So these rules allow you to turn multiplication into addition and division into subtraction, which are computationally easier. Now, I'll do a couple of examples out of your book. So here's one. Now, the book doesn't really have you do any of these examples where you see the point of these, which is you can use these rules to do computations in an easier way. It's kind of not important anymore because we have machines that do that. Unless you become the person designing and making the machines, then you need to understand this. So here's an example out of your book. You've got the base 6 log of 18, plus the base 6 log of 2. And we're to evaluate this using the product law of logarithms. Now, when I go to try and evaluate this without using the law, I'll find that the base 6 log of 18, so I've got 6 as my base, and I'm trying to find the exponent, where 6 to that exponent is 18, and that's going to be very difficult. And also the base 6 log of 2, so I'm trying to find the exponent that I have to raise 6 to turn it into a 2, also difficult. So how can using this rule make things easier? Well, if we apply the product rule, the sum of the logs is the log of the product. So we're looking at this rule here, but notice we're kind of using it backwards, because on the left I've got the sum, here on the right I've got the sum, so on the right I'm going to have the product. So that's going to be equal to the log of 18 times 2. Now, why would that be any easier? Just watch. 18 times 2 is 36. And this is the base 6 log that we're doing. So I want to know what is, let's say that that's y. What is the base 6 log of 36? Well, let's rewrite this in exponential form. 6 to the y is 36. Now it becomes kind of obvious. What exponent must you raise 6 to get 36? It's a 2. 6 to the 2 is 36. Therefore, y is equal to 2, which makes this equal to 2. So the base 6 log of 18 plus the base 6 log of 2 is equal to 2. If you'd use your calculator to do that, you'd have to go the log of 18 divided by the log of 6 gives you this decimal here, plus the log of 2 divided by the log of 6. Now, I think I hit my log button first, so this doesn't work like that. 18's log divided by 6's log plus 2's log divided by 6's log, and all of that gives us a 2. So you can see the calculator had to drag all those decimals through to accurately figure out what this was. However, using this rule, we've identified that we can turn the sum of the logs into the log of the products. Do another example from your book here. The base 10 log of 2 minus the base 10 log of 200. So let's do this two ways. We'll do it with a calculator, and I'll write out the steps, and we'll do this using log rules. So if I use a calculator, I've got the log of 2 minus the log of 200. So I'm going to take the log of 2, and that is 0.30103 minus the log of 200, which is 2.30103. And then when I do the subtraction, it gives me a 2. Okay, Let me try and do that without a calculator. So I'll do this using log rules. If I use log rules, then the log of 2 minus the log of 200 is going to be equal to the log of 2 divided by 200. Now 2 divided by 200 is the same as 1 divided by 100. I just divided top and bottom by 2. And 1 divided by 100 is decimal 0.1. Now the base 10 log of decimal 0.1 is 2, because 2 is negative 2, sorry. And yeah, this is a negative as well, right? That was 0 minus 2. Humble apologies here. This is a negative 2 because 10 to the exponent negative 2 gives me 1 over 10 squared, which is 1 over 100, or decimal 0.1 as required. So from this textbook example, you can, without using your calculator, determine this. I don't know why they missed the point entirely and don't actually show you how to use these to avoid multiplication and long division. However, whatever. They write these books to sell them to make money, not to actually teach you math. All right. One more example out of your book, and we should be good. So here's sort of a longer question. We've got the log of x squared plus 7x plus 12 minus the log of x plus 3. Okay, and again, this isn't real math. This is just a puzzle they made so that you can use a bunch of rules that they've taught you. Anyways, we'll work our way through it. So you've got the log of x squared plus 7x plus 12 minus the log of x plus 3. From here, you can use the product rule. Remember the product rule, and I'm rewriting these a bunch of times on purpose so that you learn them and don't need to write them down after. The log of a minus the log of b is equal to the log of a divided by b. So I wrote it the other way now instead of putting the log of the product on the left. Okay. So all of this is equal to the log. I guess I can erase that. All of this is equal to the log of x squared plus 7x plus 12 divided by x plus 3. Now, how is this any easier to do than that? Well, I'll show you. It's going to be a little bit simpler because this is going to be factorable. Numbers that add up to 7 and multiply to 12 are 3 and 4. So we can factor the top and end up with x plus 3 times x plus 4. And if we divide that by x plus 3, those are going to cancel each other out, with the restriction that x is not ever equal to minus 3. So all of this is equal to the log of x plus 4. So we have dramatically simplified that, where x is not equal to minus 3. But it's a log, so x can't be equal to... Well, I suppose otherwise you would have been able to make it equal to minus 3, because that'll give you a log of positive 1. So what would this look like if you were to graph it? Log looks like this. Log x looks like that. And so if we add 4, it's going to shift it 4 units this way. So our asymptote would now be there. And it would look like this, where... except x is not equal to minus 3, so we'd have a hole in the plot. Okay. So here I was simplifying this complicated looking mess by using the quotient rule. The difference of the logs is equal to the log of the quotient. Again, I'll just write those rules out one last time. And remember, it all has to be the same base. The log of a times b is equal to the log of a plus the log of b. And the log of a divided by b is equal to the log of a minus the log of b. And you can use these rules to simplify situations as they arise. The main point again is to allow you to successfully do division or multiplication by turning it into addition and subtraction after you've converted it into a log, and then you can convert it back to get your answer.